Good evening to everyone. In this section, we shall look at Cartesian Product of Set. When we talk of Cartesian Product of Set, we know that points in the Euclidean plane are defined by the set R by R. Now what it means is that if you have a plane, now let me say that the Euclidean plane is the same as the Cartesian plane. The difference is that using the Cartesian plane, with the Cartesian plane, we have to do with the x and the y axis, where the x-axis extends infinitely to the right and also infinitely to the left. The same applies to the y-axis, which also extends infinitely upwards and infinitely downwards. What it means is that when we talk of the x values start from negative infinity to positive infinity. That's for the x-axis. The y-axis also starts from negative infinity and ends at positive infinity. And all these values on the x-axis and the r-axis are real numbers. They are real numbers. Therefore, when I pick this Cartesian plane, 0, 1, 2, 3, it goes on and on up to infinity. Negative 1, negative 2, negative 3, on and on up to infinity. Positive 1, 2, 3, 4, on and on up to infinity. And the same thing applies down. Now looking at this plane, all this is called a plane. All this is a plane. And in this plane, we can have an infinite number of points. Infinite number of points. For example, I can have a point like 2, 1. I can have another point like this is 2, 1. I can have another point like 3, 2. Another point is negative 1, 1, negative 1, 4. Then you can see a lot of points. We have infinite number of points in this plane. All these are points. The points in this plane are infinite. Therefore, we can say that if we take any element in the first set, which is the set belonging to the x-axis, and we pair it to another set in the y-axis, which also contains the set of real numbers, and it means that we are going to have R combination R, and that is going to give us, and the total number of pairings we can get from this set and this set is what we call R squared. So it means that the Cartesian product of this set and this set are the total number of different ordered points that this x-axis, the elements in the x-axis paired with the elements in the y-axis can generate. So for example, let's say I have set A, which contains only 2 sets. For example, 1 and 2. Then I take set B, which contains only 2 elements. That is also, let's say, 0 and 3. Now, from these two sets, we take this to be the first set, x, and the second set, y. If we are on a Cartesian plane, we can form a Cartesian product of these two sets. It means that I can pair 1 with 0. I can also pair 1 with 3. I can pair 2 with 0. And I can also pair 2 with 3. So what have I gotten? You can see that I have gotten 4 different ordered pairs. So if I want to plot this on the Cartesian plane, it's going to be something like this. To plot this on the Cartesian plane, let me draw my Cartesian plane again with my y-axis and my x-axis. This is my origin. So I have, let's see, 1, 2, 3. I have positive 1, positive 2, positive 3. The negatives are down. Because I don't have any negative, there will be no need to introduce the negative values. So let us start plotting. My first plot is going to be 1, 0, which is going to be this. The next one is going to be 1, 3. That is going to be this. The next one will be 2, 0, which is this. And the last one is 2, 3, which will be this. So you can see that I can form a rectangle with these points. I can form a rectangle with these points. Now the rectangle I am getting is the graph of the Cartesian product. This graph is the graph of the Cartesian product of 1, 2, and 0, 3. What it means is that looking at all this Cartesian plane, the Cartesian plane has infinite number of elements ranging from negative infinity to positive infinity, ranging from negative infinity to positive infinity. But if I pick only 1 and 2 from the set of the x-axis, that is only 1 and 2 from the x-axis, and I also pick 0 and 3, 0 and 3, 0 up to 3 from the y-axis, then using only these two sets, we are able to generate a plane, which is a finite plane. This is a finite plane, which is bounded by these points. All the points on this rectangle is also part of the Cartesian product. It's part of the Cartesian product. And even points inside, any point inside is also part of the Cartesian product. So all these are points inside the set of 1, 2 for A and 0, 3 for B. Remember that this is not the only set. 1, 0, 1, 3, 2, 0, 2, 3. That is not the only set. But we are assuming that we are picking only integers. But if you want to pick all real numbers, then remember that from 1, 0, I can move to 1.1, 0, 1.2, 0, 1.111, 0, and so on. So there are infinite numbers in between 1 and 2. And there are also infinite numbers between 1 and 3. And all these points, and even there is also infinite numbers inside this rectangle. And all these points inside this rectangle is what we call the Cartesian product of the sets 1, and 0, 3. So now let's look at it. R squared, that is, whenever you have two sets, the Cartesian product is given as R squared. That is equal to P is equal to XY, where X and Y are real numbers. So that is what I said. The values on the x-axis are real numbers, and the values on the y-axis are also real numbers. So when you pick any real number on the x-axis and you pair it with a real number on the y-axis, then you are going to get r cross r, and that is the same as r squared. So let's take note of that. Using similar notation, the Cartesian product of two sets, S and T, is defined as, so this time, if we assume that the two sets are S, so S contains some elements, and T, which will also contain some elements. So S cross T is equal to P, such that P will be equal to ST. So when I find the Cartesian product of S and T, I am going to get an ordered pair, which is S and T, where this S is coming from the set S. So small s is coming from the set S, and small t is coming from the set T. So for example, if I have the set S to be, let's say, 1, 2, 3, then I have the set T to be equal to, let's say, 2, 4, 5. Then the Cartesian product of S and T, ST, that is S cross T, can give me an element like 1 and 5, where 1 is coming from the set S and 5 is coming from the set T. I can also get another pair like 2, 4, where 2 is coming from the set S and 4 is coming from the set T. Now take note that if you are finding ST, that is the Cartesian product of S and T, we don't select the T values first. No, we always pick an S value and pair it with the T value. Therefore, the pairs must be orderly arranged. So we say that a Cartesian product is an ordered pairs. That is the key word, ordered pairs. Ordered pairs of elements S and T, where the first member of each pair always from the first set S, and the second member always from the second set T. So an example is the set 2, 4 cross 2, 4, 7. So you realize that we will pick the first value 2 and pair it with the first value in the second set. Then that same first value will pair the second one, 2, 4. First will pair the third value. Then once we are done with all the first in the first set, we come to the second value in the first set. So 4 also pairs the first, 4 pairs the second, and 4 pairs the third. And all these are the ordered pairs or the ordered combination of these two sets. And this is what we call the Cartesian product of these two sets. Now let's look at some characteristics of the Cartesian product. Now the first property or the characteristic is that two elements of the product S cross T are equal if and only if they are identical. Now what it means is that if I pick a Cartesian product, let's say I pick the set S let's say I have set S to be equal to 1 and 2. Then I also have set T to be equal to 3 or 2 and 3. You know that forming a Cartesian product from these two sets, each element is going to be unique. So for example, when I start, I will get 1 and 2 as one of my products. I can also get 1, 3 as another product. I can get 2, 2 as another product, and finally I can get 2, 3 as a product. Now you realize that in each of these products are unique, because if I want to plot 1, 2 on the Cartesian plane, 1, 2 will be this. 1, 2, 1, 3 is going to be this. So you can see that each point differs. 2, 2 is this, and 2, 3 is also this. Did I plot them well? 1, 3. I have 1, 2. Then 1, 3. I have 2, 2. Okay, the 2, 2 is wrong. Let me correct the 2, 2. This is supposed to be 2, 2. Then 2, 3. So this was a mistake. Alright. Now these are the Cartesian products. So let me just use a line to indicate the region. Good. So this very box is the Cartesian product of the set 1, 2 and 2, 3. Now because 1, 2 and 2, 3 forms a Cartesian product in this region, what the first property is saying is that if you pick any point either on the rectangle or inside the rectangle, any point at all you pick will differ from the other. 2 points cannot be the same. The only way 2 points can be the same, for example, if I pick a point P in this rectangle, if I pick a point P, if I pick a point P in the rectangle to be, let's say, I have a point like 2, or let's say 1.5, comma 1.5. This point will be in the rectangle. If I pick this point and I pick another point Q in the rectangle, I can pick a different point. If I pick a different point PQ, that is, let's say, A and B, the only way I can say P, this point is the same as Q, is when A is 1.5 and B is also 1.5. So all what this property is saying is that you can't have two different points being the same in a Cartesian product. The only way they can be the same is when they are the same point. So it means that for P to be the same as Q, Q must also be 1.5 and 1.5. That is the concept here. So we are saying that the only way ST can be equal to AB is when S is equal to A and T is also equal to B. So that is one characteristics of the Cartesian product. 2. If the set S is an empty set, or T is also an empty set, then S plus T will also be an empty set. If I give you an empty set, let's say set S is an empty set, there is nothing in it. and I give you set T, let's say containing 1 and 2, and I ask you to form an ordered pair or plot the points in S against T, the question you ask yourself is that, what are the elements in S? There is no element in S. Therefore, you cannot plot any element in S against T. Therefore, S cross T is going to be equal to an empty set, or this. So that is the second property. Let's take note of that. Whenever you have two sets whereby either all the two sets are empty sets or one is an empty set, the Cartesian product of those two sets will also be an empty set. That will also be an empty set. The third property is that S cross T is not equal to T cross S. It's not equal to T cross S. And that one is very simple. We should know that. Let me explain it briefly. Now, let's say you have a Cartesian product. This is the Cartesian product of the entire plane from negative infinity to infinity. If I pick any point at all, for example 2, 1, and I plot it, 2, 1 is not the same as 1, 2. You can see that 1, 2, the point there, let's say the point there is A, and 2, 1, the point there, this one is 1, 2, and this one is 2, 1. And you realize that these 2 points are not the same. So we are saying that Cartesian product is not commutative. S cross T is not the same as T cross X, all things being equal. All things being equal, they are not the same. So let's demonstrate with another example. If you have A, set A to be 2, 5, and you have set B to be equal to, or let me write it this way, set B to be equal to, let's say, 2, 4. Now you realize that our Cartesian product of A and B is going to be 2, 2, 2, 2 as one product. You will have 2, 4 as another product. You will have 5, 2 as another product, and we will have 5, 4 as another product. Now let me pick values that can bring let's say you have 2, 5, and you also have 5, 2. Or yes, you have, let's say B is 5, 2, and you want to plot this. We can have A cross B to be equal to 2, 5. We will have 2, 2. We will have 5, 5, and we will also have 5, 2. So these are the combinations. Now you realize that in this Cartesian product we have 2, 5 here, we have 5, 2 here. This 2, 5 is not the same as 5, 2. This 2, 5 is not the same as 5, 2. Another way of also demonstrating this, another way of demonstrating whether S cross T is the same as T cross X is to take it this way. Let's say you have the set A to be 1, 2, and you have the set B to be, let's say 3, 4. Now let's find A cross B. A cross B is going to be equal to 1. This is 3. So we have 1, 3 as 1. We have 1, 4 as another 1. We have 2, 3. 2, 3, and finally we have 2, 4. Now this is for A cross B. Let us find B cross A. To find B cross A, remember we are using ordered pairs. So our first set becomes B, then the second becomes A. So we can have a combination like 3, 1. We can have a combination 3, 2. We can have a combination 4, 1. And we can also have a combination 4, 2. Now look at these values. Look at these values. You realize that these sets is different from this. The two combinations are not the same. 1, 3 is different from 3, 1, because if I should plot 1, 3, if I should plot 1, 3 here, I'm going to get 1, 3 is going to be this. But if I should plot 3, 1, I'm going to get this. So the 2 points are not the same. If I plot 3, 2, I'll get this. But if I plot 2, 3, I'll get this. So you realize that the combinations are not the same. 1, 4 will give me something like this, but 4, 1 will be here. So you can see clearly that B cross A is not the same as A cross B. B cross A is not the same as A cross B. So that is one aspect of it. Now let's move on to the next 10. The fourth one, the Cartesian product of n sets, that is S1, S2, S3, up to Sn. Now what we are saying here is that if the number of sets is not 1, let's say we have the first set, let's say AB, then we have set B containing PQ, then we have set C containing, let's say, XY. So we have 3 sets. In this case, we are saying that we are supposed to pair each element to each. We have to find the ordered pairs. Remember that this is going to be your first value. So if I want to pair this one, it's going to be, you take the first element A. Let's say we are finding A cross B cross C. So this one is called the Cartesian product of 3 sets. You take A first, then it will pair P. So A, then P, then also X. That will be your first one. Then you take A again. That's the first set. Then it will pair P. Then this time it will pair Y. Now I am done with X and Y. I will take the first A again, which is A. This time when I take A, it will pair Q. Remember the first one, it paired P. So this time it will pair Q. Then it will pair X. Are we okay? So we have A pairing P and X, A pairing P and Y. Are we okay? Then we take A again, A pairing Q and X, A pairing Q and Y. So we have another one. A pairs Q and pairs Y. Pairs Y. Now we are done with the A. So we are going to take the B also. Then the B will also pair P and pair X. Then the B again will pair Q. No, sorry. The B again pairs P. Then it will pair Y. Then we take the B again. This time it will not pair P, it will pair Q. Then pair X. Then finally, the B will pair Q and pair Y. So you can see that this will be the total Cartesian product of three sets containing these elements. You realize that A contained two elements, B contained two elements, C contained two elements. So if I take 2 times 2 times 2, I'll get 8. And that will give me the total number of products. That will give me the total number of products, which is 8. So here, what the property is saying is that a Cartesian product of n sets, S1, S2, S3, up to n number of sets, is the set of n tuples. That is S1 times S2 times S3 times S up to n, where X1, S2, S3 belong to the set of S1. Then S2 belongs to the set S2. Then we perform the combination just like I have done. If you read this one, you will not understand it clearly. But that is exactly what I have done here. So it is an ordered pair of each element in the first set to the second and the third. And even if they are 4 sets, you must orderly arrange them. So that is just the concept. Now let's look at this example. Example 1. We are to prove that A cross B is equal to B cross A if and only if A is equal to B, or at least 1 is an empty set. So we are proving 2 things here. Let's focus on the empty set. Now we are saying that let A be equal to B. Now we are making an assumption that A is equal to B, or at least 1 is an empty set. Remember that we have already proven that in Cartesian product, A cross B is not equal to B cross A. We proved that. We have already proved that here. But in this question, we are saying that the only condition for A cross B to be equal to B cross A is when either A is equal to B, or at least B or A is an empty set. So let's start with this. If A cross B is equal to B cross A, then let's come here. On the other hand, we are saying that let's make an assumption that if A is an empty set, because that is the assumption that the question has given us, that the only way that A cross B can be equal to B cross A is when one of A, either A and B both are empty. Either both are empty or one is an empty set. So here we are making an assumption that let A be equal to an empty set, or let B be an empty set. If A or B is an empty set, then it implies that A cross B Because either A or B is an empty set, A cross B will also be an empty set. We prove that. Then B cross A. Because B or A, one is an empty set, B cross A will also be an empty set. If A cross B is empty and B cross A is also empty, then it means that empty is the same as empty. Therefore, A cross B is the same as B cross A. So we have been able to prove that. This implies that A cross B is equal to B cross A if one of them or even all of them are empty, then A cross B will be equal to B cross A. So that is the proof for the empty set. A cross B is equal to B cross A. Now we are done with the first part where we are proving that the only condition for A cross B to be equal to B cross A is when either A or B is an empty set. That is the proof. Now we are also supposed to prove that another condition for A cross B, another condition for A cross B to be equal to B cross A is when A is equal to B. If A is equal to B, then we can also say that A cross B is equal to B cross A. So let us prove that. Now let us assume that A cross B, when you find A cross B, it is going to generate some element, let's say, ordered pair xy. What it means is that we are assuming that xy belongs to the set of AB. So let me put it this way. Xy, this ordered pair xy belongs to the cross product of, or the Cartesian product of A and B. So xy belongs to this set. Now, because A cross B is the same as B cross A, then we can also say that that same xy must belong to B cross A, must also belong to B cross A. Now, in this case, this assumption here, we are making an assumption that A is not an empty set and B is also not an empty set. Let's take note of that. So if A is not an empty set and B is not an empty set, then it means that there is an ordered pair. There is a Cartesian product which belongs to the set A cross B, or A cross B. Then there is the same Cartesian product, that is xy, that belongs to B cross A. Because B and A are not empty sets, there exists some pair of elements generated by the combination of A cross B and B cross A. And because we have made an assumption that A cross B is the same as B cross A, then it means that the same element that belongs to A cross B is the same element that belongs to B cross A. Now, because we are dealing with ordered pair, it means that if xy belongs to A cross B, then it means that the first value, which is x, belongs to A, and the second value, which is y, belongs to B. Then when we also come here, if y belongs to B cross A, then it means that the first value, which is x, belongs to B, and y also belongs to A. Now let's look at these two statements. What do we see from here? We are seeing that x belongs to A. Here we are saying that x belongs to B. If x belongs to A and x belongs to B, then it means that A is a subset of B. Then if y also belongs to B, and y belongs to A, then it means that B is also a subset of A. Now, if A is a subset of B and B is a subset of A, the only condition that A can be a subset of B and B can also be a subset of A is when A is actually equal to B. And hence, the only condition that A cross B can be equal to B cross A is when A is equal to B, or A is an empty set, as proved here. So these are the only two conditions. Example 2. Let the sets A, B, and C be defined in each of the following. So we have A, B, and C, and we have to find the Cartesian product in each case. So let's start with the first example. The first example is this. We have to find the Cartesian product of this set. Now, before we find the Cartesian product, we can make a rough work. Remember that the first set contains 2 elements, the second set contains 2 elements, and the third set contains 2 elements. So by all means, we know that because we are dealing with Cartesian product of 3 sets, it is going to be A to the power. So there are how many elements in each set? That is 2. So it's going to be 2 times 2 times 2, and that will give us 2 cubed, which is the same as 8. It means that the number of A cross B cross C is going to be equal to 8. What it means is that after solving, we are supposed to get 8 different ordered pairs of products. This one is just a guide. In case of objective, if they tell you to find the number of products generated from this set, it's going to be 8. But that is not the solution to this question. So let's start. Now, to start, we are finding A cross B cross C. And this is going to give us the first combination. Will take X1 to pair Y1. Then it will also pair Z1. That is the first one. Then we will take X1 again to pair Y1. X1, Y1. Then this time it will not be Z1, it will be Z2. I'm supposed to separate them with commas, but I'm just ignoring it. I don't want it to be stuck. Then the next one is going to be X1 again. Goes with this time, not Y1, Y2. Then Z1. Then I'll take X1 again. This time, still Y2, then Z2. Now I am done with the X1, so I'm going to start with X2 this time. So I have X2 going with Y1, then Z1, then X2 again, going with Y1, then Z2, then the same X2 again, going with this time Y2, then Z1, then finally X2 goes with Y2, then Z2. So these are the ordered pairs. These are the ordered pairs, and this is what we call the Cartesian product of these three given sets. That is the first example. There are three. I'll solve the second one, then I'll leave the last one for you to try. Let's take this one. So to find the Cartesian product of this, we are finding A cross B. You can do a rough work to see that A cross B is going to be the number of A cross B is going to be, if there are two elements in the first set, so 2, times there are 3 elements here, 3. 2, 3 will give us 6. So we are going to get 6 different products from A cross B. So we can start. The first one will be X1, Y1. Then we have X1, Y2. Then we have X1, Y3. We are done with the X1. Then we come to X2, Y1. We have X2, Y2. Then lastly, we have X2, Y3. So we have 1, 2, 3, 4, 5, 6. That is exactly what we have here. You may try the last one. Try this last one. Now let's solve the example 3. We are to prove that A cross B cross C is equal to A cross B, A cross into bracket B cross C, if and only if at least one of the sets A, B, and C is empty. So here we are saying that the only condition for this very set to be equal to this very set is when at least one of the sets A, B, and C is an empty set. So let us make an assumption here. Let A be an empty set. Let A or B or C be an empty set. So we are making this, let A or B or C, be an empty set. So we have made an assumption that either A or B or C is an empty set. If that is the case, then we know from the characteristics of Cartesian product that A cross B cross C, if A is the empty set or B is the empty set, then A cross B will be an empty set cross C. And we know that an empty set cross C will also produce an empty set. Now, let's also take the second part. For A cross into bracket B cross C, if A is an empty set, then we are going to get an empty set. Then we are going to get an empty set cross B cross C. Remember that an empty set cross any set still produces an empty set. So remember that an empty set is equal to an empty set. This set is the same as this set. So because this set is the same as this set, we can conclude that, therefore, remember that A cross B times C is giving us empty, and A times B cross C is also giving us empty. Since the two sets are giving us empty sets with the assumption that one of them is an empty set, then we are going to conclude that, therefore, A cross B cross C is equal to A times B cross C, based on this given assumption that A or B or C is an empty set. So that is the proof. Now, we can also prove this by contradiction. So let's take this. Proof by contradiction. Proof by contradiction. Now, when we say proof by contradiction, remember that the question says that the only way A cross B cross C will be equal to A cross B cross C. The only way these two given Cartesian product will be the same is when at least one of the sets A, B, and C is empty. So that is the statement. One of the sets should be empty. But we are going to contradict the statement and say that let A not be an empty set. So we are assuming that A is not an empty set, B is not an empty set, and C is also not an empty set. So it means that the statement which says that A, B, and C should be an empty set, we are making a counter statement that they are not empty sets. If they are not empty sets, then it means that their Cartesian product will result in some ordered pair. Is that right? Therefore, we can say that, let's see, X and Y is an ordered pair by combining A cross B to what? C. So we can say that then let X and Y, which is an ordered pair, belong to the cross product or the Cartesian product of A cross B cross C. In this case, we can say that, remember that this is one set on its own and this is the second set. Remember that this is the first value and this is the second value. Because we are ordered pair, then we can say that X must belong to the first set, which is A cross B, and Y belongs to the second one, which is C, the set C. Now, also know that the statement is saying that A cross B, A cross B into bracket cross C is equal to A cross into bracket B cross C. Because these two sets are the same, if X, Y belongs to the first one, then it implies that X, Y, that same ordered pair, belongs to the second one too, which is A cross B cross C. Because the two sets per the question are the same. Now, if this statement also holds, then it means that the first value is for the first set, and the second value is for the second set. Therefore, we say that then F belongs to the first set A, and X also belongs to the second set, which is B cross C. Now, remember that we made an assumption that A is not an empty set, B is not an empty set. and C is not an empty set. If A is not an empty set, B is not, and C is also not an empty set, then it means that per the definition of Cartesian product, remember that A cross B is not the same as B cross A. The only way A cross B and B cross A can be the same is when either A is equal to B or A or B is an empty set. We have proven this in our example 2. So now let's see something. We realize that in this case, we saw that X belongs to A cross B here. Then here we are seeing that X belongs to A. Now the statement X belongs to A cross B and X belongs to A. These two statements are contradictory. The two statements are contradictory because X belonging to A cross B, so the A cross B is a different set, and that same X belonging to A makes the statement contradictory. Now, remember that A cross B must produce an ordered pair. Therefore, this X is an ordered pair. Ordered pair. But this A is just a set. Therefore, X here is just an element. An element. This X here belongs to set A, so it is just an element. But this X here belongs to the cross product of A cross B, so it is an ordered pair. How can an ordered pair be an element? So you realize that this X here says it is an ordered pair. This X is also saying it is an element. An ordered pair cannot be an element. So this entire statement is false, or it is contradictory. Because it is contradictory, it means that the assumption we made here is also a false assumption. So we cannot assume that A is not equal to an empty set, B is not equal to an empty set, C is not equal to an empty set. Therefore, we conclude that A should be an A or B or C must be held an empty set. And that is the right statement. The only condition for A cross B cross C to be equal to A cross into bracket B cross C. That is when A or B or C is an empty set. If you make this assumption, you will end up contradicting yourself here. Now let's move to example 4. Now example 4 says we should sketch and describe the graph of A cross B, that is the Cartesian product of A and B in the xy plane. In the xy plane. So here we have A. A is from 1 to 2, and B is from -2 to 3. Since we are done with the xy plane, here was supposed to be y, not x. The second set is supposed to contain the element of of y. So we are going to find all the ordered pairs. Remember that from 1 to 2 is infinite because we will have 1, then maybe it goes on to, let's say, 1.5. Then it goes on and on to 2. There are lots of elements in between 1 and 2. So you may have the first set to be there. And the second set is also from -2. It can goes on. You get -1. It goes on and on. You will have -2, or even 0 will come. So -1, you will have, let's say, 0. Sorry. You have 0. Then maybe go on 1. You will have 2. Then finally 3. I'm using the dotted lines to indicate that in between any value that is from 1 to 1.5, we have infinite number of values. From 1.5 to 2, we also have infinite number of values. From -2 to 1, we have to -1, we have infinite number of values, and so on. So if I want to pair this using the Cartesian product A and B, let's say this is our A, this is our B. A cross B is going to be infinite. So we can have a point like 1, then comma -2 as one of the points. We can also have 1, 0 in it. We can even have 1 and 3. I'm not listing all because we can't list all. We can also have 1.5 to -2. We can even have 1.5. Let me select this part. We can have 1.5 to, let's say, 0. We can have 1.5 to 3. We can even have 2, -2. We can have -2, +2, sorry. It can go to 1. And we can finally have 2 to 3. Please, let me stretch on that. There are infinite numbers in between these. Infinite numbers in between them. We can't list all. We even have decimals and so on. So the numbers there are infinite. So if you are asked to sketch the graph of this, you can't list all. So you just use the dotted line to indicate that they are infinite. The most important thing is that you have to take the vertex. That is, the first one, 1, will pair -2. Then the 1 will pair the last value, which is 3. Then the 2 will also pair the first value, -2. Then it will also pair the last value, which is 3. So 2 pairing 3. These are the vertex. So this will be like the boundary, but we have infinite numbers within it. So if I want to plot, let's plot the vertex first. 1, -2 will be here. Then we have 1, 3. 1, 3 will be somewhere here. Then we will have 2, -2. 2, -2 is here. Then finally we have 2, 3. So 2, 3 will also be here. Then after that we can join with a straight line. Let me use a different color. We'll have this to here, to here, then finally we join it here. So this is the Cartesian product of this given set. The Cartesian product of this given set. This region. And you realize that just within this rectangle, we will have infinite number of points. So some of the points we can locate is the 1, -2. So we can have 1, -2. 1 will be 0 is here, so 1. 1 -2 will be somewhere here, so it is on it. We can have even 1.5. We will have 1.5 here, 1.51, 1.52. We can even have 1.6 something. We can have 1.7 something. So we can have a lot of points just within this rectangle and on the rectangle. And all those points is what forms the Cartesian product of 1 up to 2 and -2 up to 3. Because within 1 and 2, we have infinite number of elements. -2 to 3, we have infinite number of points. And all those points are what we are seeing. They are the points we are seeing in the rectangle. Infinite. So that is the graph of this Cartesian product. So let's do this exercise, then we close this lesson. Let's just do the first one, then you will try the second one. So we are solving this. Let A be equal to 1 to 3. 1 to 3. So 1 to 3 means from 1, there are infinite numbers between 1 and 3. There are negative numbers, decimals. You can have 1.5, 2.5, 2.6, 2.07, a lot of numbers in between 1 and 3. The same thing applies to 2 to 3. There are infinite numbers. So we cannot list all the Cartesian products. So the best thing you need to do is to find the vertex. The vertex is going to be the very first value. That is going to be 1. Will pair 2. Then it will go on and on. Then 1 will pair 3. Then it moves on 3. 3 will also pair 2. Then it goes again. Then finally, 3 must pair 3. So that is going to be it. These are the vertex, the end points. I am using the dotted lines to indicate that it continues up to infinity because in between 1 and 3, there are infinite number of values. In between 2 and 3, there are infinite number of values. So that is going to be the concept. Now from here, let's plot this on the graph. So we have 1, 2. The next one will be 1, 3. The next one is 3, 2. And the last one is 3, 3. So you realize that our graph will be this. That is going to be the graph. So this portion represents the Cartesian. This portion represents the Cartesian product of the given set. What it means is that all points on this will satisfy the graph. Every point here will satisfy the graph, and those points inside and on the graph is what we call the Cartesian product. So one of the points can be, let's say, 2 and negative 2.5. They can locate 2.5 inside. Therefore, 2.5 is part of the Cartesian product. They can also see, let's say, 2.5 and let's say 2.5 and let's say 2 is also another point. You can have more points, for example, 3 and 2.5, 3 and 2.6. Any number in between 2 and 3, we can use it. Any number in between 2 and 3 here, we can use it. So all points here is within the Cartesian product, and that is exactly the graph. I'll leave the second one for you to try. So let's end today's lesson and continue next time. Thank you.